Hello everyone, my name is Arpi Sahakyan. I'm going to present today the topic, how to start thinking critically. This topic is going to cover three aspects of thinking critically. Misleading statistics, we are going to talk about biases in data, and multiple testing. This is a talk for beginners, people who want to start in the field or are beginners in the field, so it's not too late to leave now. Other than that, I'm going to start. So I'm going to just show you the numbers that are in the open source data sets. You might have seen them before. I'm showing you this slide just to point out the large scale of numbers that are in the open source data, so data that is publicly available to everybody. Because in the later slides, you might have the question, why isn't this so obvious to us? If we are having this bias, isn't it such an obvious thing to see in our data? Well, it's not that obvious to see when your scale of data is so large. So I'll start about our intuitions in mathematics. We all have, as humans, an ingrained intuition in mathematics. We know in our daily life how likely some things are and how unlikely things are. But when you use this intuition on a very large scale of data, it can really misfire and be very erroneous. So I'm going to give you a very simple example here for statistics. Consider that we have 23 people and we are asking what is the probability of at least 2 people having the same birthday, same date? And most people, I think, would think of this problem and say there's 365 days in the year. There is no way, the likelihood is very low that 23 people are going to have the same birthday in a year. But in fact, when you do the statistical calculation, the number is 50%. So it's like tossing a coin. That's quite a large number for a lot of people. If you are interested in how to solve this problem, you can follow the link here. And I'll give you a more complicated example where our intuitions can be wrong. So imagine we have 2 hospitals, Hospital A and Hospital B. We have 1,000 people have been applied to both hospitals. And we know that 900 have survived in Hospital A, and 800 have survived in Hospital B. Now, simply looking at this statistic, you are going to say, all right, I'm going to apply to Hospital A as a patient because it seems from the statistics that they are having a better survival rate. What if I tell you that's not the whole information? Not every patient that enters the hospital has the same level of critical condition. Some are more sick than others. So in Hospital A, people in critical condition were admitted 100 people that day. Out of them, 30 survived. And in Hospital B, 400 people with critical condition and 210 survived. Now this changes everything, right? So we're going to Hospital B from now on. They have a better survival rate for the critical condition patient. It means Hospital B is more specialized. We're going here for sure. Now, this is called the lurking variable in statistics. It is a hidden context. It's a condition that you look at the face value of the numbers, and you have an assumption that this is how the statistic is, this is our ranking. We can have this problem in so many fields, like choosing Amazon products, looking at any sort of rankings, and have the perception that the numbers we're seeing are representing what the real truth is. So I'm going to classify the sources that from often misinformation into 3 different types, and we are going to cover a lot of these things. So first source of misinformation or misleading statistic can come from generating the data. So which means this is the part where we are gathering data. In any sort of way. It could be scraping or polling. So we can have bad or biased sampling here. We can have loaded questions, faulty polling. By loaded questions, I mean that when you are surveying a number of people, it is quite an art to create a survey that isn't misleading or taking the person's mind into a certain direction. The number of questions, the order of questions, and the formulation of questions is very important in a survey. So simply hearing that a survey of 1,000 people has decided that this is our conclusion isn't enough. We have to understand who this survey was who the survey was made by, and what were the questions asked. The next part is processing data. Here we can have cherry picking, significance, and quality of the data, and data mining. This is the part where we are getting our raw data and we're making it more readable for our next step of visualization, which is the communicating data. So we are presenting the data that we have gathered in the form of charts, graphs, or reports to the audience. And here we can have issues with data visualization, wrong causality, and hidden context. Now we're going to talk about a lot of these things in the next slides, but before I move on, I'm going to have a disclaimer. I'm going to show you data and charts that come from real life. I have modified the images to remove any sources or logos from the images. The reason is that I don't have an agenda. I don't have any political affiliations. I'm just showing you real examples of misleading information that will be shown to the public. I don't want to go into what the chart is about. All right, so the first and the most simple, basic way we can present data to the public is a pie chart. And the obvious thing about a pie chart is that it has to sum up to 100, right? In this one, it obviously doesn't. Not only doesn't it sum up to 100, the other thing that's important about a pie chart is that the proportion of the slice has to be correct to the number that's written on it, right? If we're saying something is 50%, it has to be half of the pie. So in this pie chart, we're looking, it looks like the green slice is the largest, but it says the lowest number. So we have two aspects of the pie chart very wrong here. So I'm not saying that this information was presented to the public in order to mislead or lie to them. It could have been just a wrong chart, choice of chart. I think what happened there is people were allowed to choose several candidates, and they have presented it in the wrong chart. So they could have maybe used the bar chart, and it would have been a better result. Speaking of bar charts, I have two bar charts here that are presenting the same exact information, but they look drastically differently. So what we are going to look for in a bar chart, that both axes are labeled. We are going to ask the chart to have an absolutely clear numbers of on our axes, what they're representing. We want the slices of the axis to be proportional to the change that is happening. We want the numbering to be consistent, and yes, and we also want the bars to be proportional to the change that they are representing. So why does our chart look so different in those our data look so different in those two charts? Well, the axis doesn't start from 0 in the first one. So it starts from 3.14, which makes the 2008 number look 10 times less than the 2012 number. But if you look from in the next chart when it starts from 0, this change is very small. So this can be quite misleading, just showing the chart this way to the public. And this is a very funny example of the same issue, where the aim was to show the average height of females by country. And you can see that the tiny Indian women are scared probably of the huge Latvian giants. The reason here again is that the chart doesn't start from 0, the axis of the y. And the bars, which in this case are pink women, are grown proportionally, not just by height. So it looks like a real giant. Now, this is another case of a chart, and I'm sure you are not seeing clearly the x-axis, where the issue is with this one. And this is, I think, was quite intentional, actually, because the numbers are quite blurry on the chart when it was presented to the public in this exact manner. What we are not seeing in the x-axis, no, let me start from the data. So what we're seeing in the data is that we are having COVID cases that looks like they're decreasing over time. The x-axis is a timeline. What we're not seeing in the chart right now is that the numbers that are written here are not in chronological order. So they have switched the bars around to fit an agenda. So we can also have bar charts lying down, but they should have the same rules as the other bar charts. So here we are looking at information of calories per product and comparing what is the calorie in a specific product of a company. And the company that made the chart was claiming that it is quite a large difference, when in fact it was only 70 calories less than the companies that had the most calorific food. Another thing that we're not seeing in this chart, which is a bad way of presenting us the data, what food is compared to what, and what is the portion size. All right, moving on to line charts. So in these cases, we are also going to look at the axes, but in this graph, it's quite all right. The axis is not the issue. We are going to ask for proportional distances that the numbers represent. We are going to ask for a title to see an explanation. But what is wrong with this? So this chart is showing us the expenses increasing for education, so tuition, room expenses, board expenses, and the average earning from a bachelor's degree. And just comparing these two lines, and if you look at this chart just on its own, you would think maybe it's not worth to go get a bachelor's degree. It seems like my expenses are very high, but I'm not going to get a lot of earning. What is missing from this chart is the rest of the information about the world. What is the expenses and earnings of people who are not going to the bachelor's degree? Maybe we would see that the earnings of people have really decreased. So we should be paying attention to all the context. Now, this is a funny chart made by a statistician. His name is written as a source. I don't want to say it because I might mispronounce it. But he was using real-life data to present exactly the point that I'm presenting to you now, that data can be mined and it can be represented to look like there is a correlation in some things that don't have a correlation at all. So we're looking here at number of people who have drowned by falling in a pool and Nicolas Cage movies. So yes, it looks like we have quite a correlation there. And so wonderfully put together. And are people really drowning in pools because of Nicolas Cage? And the issue here is that the data is really mined. This is called cherry picking, when you are picking a specific section of data to just represent what you are looking for. So these kind of things are important to look for, because when researchers are asked to find something, it is really easy to go after a wrong correlation and not do a complete test. Here is another one, just to make sure that you know that this wasn't a fluke. He can do this many times. He has a lot of other charts. And this is the per capita cheese consumption versus number of people who died by becoming tangled in their bedsheets. I didn't know that was possible. So again, an example of cherry picking. We are going to talk about cherry picking more later. Okay, so we have another line chart here. And in this line chart, it looks like there was some pivotal point, like in 2015 there, and something drastically happened, and there was a huge decrease in our data. That's what it looks like when you just have a quick glance. But if you look at it again, the chart is upside down. The y-axis 0 is on the top. I'm going to turn that around for you to visualize it easier, and you can see here that the numbers are indeed going up. So we should be truly looking at the Y chart every time we see any sort of representation. Moving towards hidden contexts. A lot of you would have heard this advertisement that 80% of dentists recommend, and insert name of the brand, of a toothpaste. So what they're not telling you here is how can all of these toothpaste companies claim that 80% of dentists are recommending specifically them? How many dentists, what is the percentage out there? Is it 200% of dentists? And then you figure out that the lurking condition here is that the dentists weren't asked to pick a brand. They were asked, is it good to brush your teeth or no? With toothpaste versus water. And then that was what they were answering to. And they could also pick several brands that they thought was a good brand to use. So the 80% of dentists recommend doesn't mean our brand over everybody else. They just recommend a brand. All right. Another form of information to look at when you are looking at any sort of research, you have to know who it was funded by, who it was conducted by. And in this case, the participants, they informed the participants that the research was being performed by independent research company, and in fact it wasn't. Here, this one, I think this one gets most people. So this is a nutrition label, and here we are seeing that our food product has nearly 2 calories. It has 0 fat, 0 sodium, 0 carbs, 0 sugar, 0 protein. Okay, sounds great. Yes, in fact, what is it? And then what you're not reading in this is the tiny disclaimer over there that says not a significant source of nutrients, which is less than 0.05 grams. So by law, if there is something in your food that is less than 0.5 grams, they don't have to write it on the label. Okay, so what the companies have done there is they have decreased the serving size over there to 0.49. So they don't have to write anything on the label at all. And the serving size in the container is 200 pieces. So you should really look at the items you're buying that say sugar-free. I think you would find a lot of things that are completely made of sugar but get away with saying an incorrect portion size. All right, now that was the fun part of the presentation. I'm going to move on to biases in data, and we're going to talk about confirmation bias, cherry picking, survival selection, availability, and causality biases. Now, cherry picking, we mentioned this one before. It was the Nicolas Cage movie's case, where it is a fallacy of selective attention, where we are picking specific data out of all the data that we have to represent a certain narrative. And we are underestimating the importance of the cases that are not supporting the hypothesis. What is a confirmation bias? It is actually a type of cherry picking. Confirmation bias is the tendency to search for, interpret, or favor information that confirms one's prior beliefs. So we have a belief about something, and whatever data we are seeing, we are interpreting it in a way that is confirming our beliefs. Sorry. So this is very important when interpreting any sort of data, reports, when testing a hypothesis. As a researcher, you shouldn't go into the hypothesis already having made your mind what this thing is going to be at the end. And this is one of the biases that I think we see mostly in our daily life more than others. A sampling bias, I have a funny cartoon for it. So the cartoon says that they have asked people if they liked answering surveys or no. And a lot of people have said, yes, I love answering surveys. What they're not seeing here is the people who don't like answering surveys, so they don't answer surveys. So this is the sampling bias, that it is a bias that occurs when looking at samples that are not representative of the whole population, right? You're taking a small sample of the population and then scaling it up to the whole population and claiming that this is what everybody thinks. And it can be in the cases where our data is not truly randomized. All right, so I'll give you two examples of this if you're thinking that this is not so common. So most surveys and statistics come from European countries because they are being done by European research companies. So when they say 90% of people feel this way about this topic, that's 90% of Europeans. That's who they have surveyed. And a lot of statistics are based on students because surveys are usually done for a small amount of money. Please come to our survey, we'll give you some amount of money. And students are often doing these surveys to get some extra money. All right, the next one is, how much time do I have? Okay, the next one is survival bias. Survival bias is the logical error of concentrating on data points that have made it past a certain selection point. I'm sure a lot of you have seen this graph. If not, I'll explain it. It is from the World War II, where these are the planes that are coming back to the country, and they have been harmed severely, some of them. They have like bullet holes all over them. Well, not all over, in very specific places, the bullet holes. And the army looked at the planes and said, okay, we're going to make them better. We are going to cover those parts with more armor, so the planes are more protected, and put less cover on the parts where there aren't any bullet holes to make it more mobile, a lighter plane, until the statisticians stopped them and said that you have a survivor bias here because the planes you are gathering data from are the ones that returned to your base.
I think there's only one statistician at that time they suggested them to go and check the bias.
Exactly. So this statistician said that this is the exact issue, that if you had a bullet hole in the parts where are currently white, that plane would have crashed and it wouldn't have made it back. So you should put the armor on the engine, the propellers, etc. All right. So it is typically because of lack of visibility. This is mostly for also marketing. A lot of marketing is based on the success stories of current companies. We are looking at the cases of Coca-Cola, of Adidas and other companies, and they're saying we should be replicating their strategies to get ahead in the market. Well, the truth is that a lot of these strategies have been done by other companies as well, but they have failed. The issue is that we don't know about these companies. And then the sad one example is when you're touring ruins of old cities. Most likely it is not at all what that city used to look like. These are the most stable, the most well-built buildings that have survived, and most of them would have demolished through time. Another one, availability bias. So the availability bias is the human tendency to think that examples that you can come up with readily in your mind are representative of the actual world. So if you're seeing a lot of airplane crashes in the news, but you're not thinking of that every time there is an airplane crash, it makes the news. But you are not thinking of the millions of airplanes landing safely in every country. So this kind of increases the probability of this happening in your head. So there is another example of shark bites in certain areas when the probability of shark bite in the same area reduces drastically after there is one case. But because we can recall that there was shark bite here, we're never going in that water again. Another example is hacking. If a company becomes hacked, they are most likely going to increase their security tenfold, never to happen again, but we are going to lose all confidence in the company and never trust our data to them. So the causality bias, I think people have heard about the most, like this tagline of correlation is not causation. So it is the case of overestimating the degrees of causality between two events, even believing that they are causally related. I think I wrote that wrong. Okay, I'll rephrase that. So we're estimating the degrees of correlation between two events and thinking that they are causally related, so they are causing one another. We are misregarding coincidences and misrepresentations, like in the example of the Nicolas Cage again. I'm bringing that chart up again. It would have been ridiculous to say that one is causing the other, even though we can see correlation in the data. We are not thinking of a hidden factor. There can be a third factor that is making both of these things happen, and by removing one of them, we're not going to remove the other. This is especially important in the field of medicine. I'll give you an example of cancer rate in prosperous countries. So there is an increased number of cancer in prosperous countries, and people were really looking at this statistic, baffled, thinking what is causing it? Why are people getting more cancer when they're living in a better environment? They were looking at the income and how people would distribute this income. What are they buying? What are they drinking? What are they eating? And then it turns out that the medicine in prosperous countries is better. So they are curing a lot of the diseases that would have killed you sooner. Thus, you are growing old enough to get cancer, because cancer is more prominent in old age. So correlation here didn't mean causation. So you're not getting cancer because you are in a prosperous country. And my last topic here is multiple testing. I'm going to give you just a quick introduction because it's a very large topic that is very well covered, and you can read about it more. So I'm going to present this comic by the artist XKCD, which perfectly explains the scenario. So when we are doing any sort of research, statistical research, we are having a hypothesis. We're called the null hypothesis, and we are going to test this and either confirm or reject our null hypothesis. Now, when we are doing any sort of statistical research, there is a chance that we are going to be wrong, that there is going to be a false positive, meaning that all researchers have this chance of being wrong, and then the acceptable probability for most research is called a p-value, and it is usually set to it is set to 5%, so 0.05. Now, yes, important thing to understand here that any sort of research done has a 5% chance of being wrong just by accident, even though it is actually correct. So in this comic book, we're having a rumor that jelly beans cause cancer. So they invite a scientist, they give him all the data and say, okay, please test it. We have a horrible rumor. And then the scientist tests and he says there is a probability of 95% that jelly beans don't cause cancer. Then the rumor comes back that we heard that one specific color of jelly beans causes cancer. We don't know which one. Test for all of them. There are 20 colors. We're going to test for 20 colors of jelly beans on the same data set, which means that we are increasing our probability of a false positive here. So in this next slide here, we are having a aha moment of the p-value being less than 0.05, and we're saying that the green jelly bean causes cancer. Acne, sorry. And in the next day in the news, it's the first headline that green jelly beans are linked to acne. So this is the issue of multiple testing that most researchers know, that their research has a 5% chance of being wrong. So when you are reading about studies that have a lot of factors or studies that have not been replicated, you have to understand that there is a chance that it is a false positive. This is why we have peer reviews for our papers. People replicate our results to make sure that this was not just a coincidence. Right. Thank you.
Thank you for the presentation. So if there are any questions, please raise your hands.
Thank you for a great presentation. I just want to ask, Is it working? Ah, okay. I just wanted to ask, is there any questions list that for every data you can ask for yourself to think like, for example, the p-value is really high for your measurements or the way you are thinking of a data?
Thank you for your question. That's actually a great question, and it would be wonderful if there was such a list. Unfortunately, at least I don't have one. I don't know if it exists. But there are known biases that we can find in our data. This is just some of them. There are a lot more. And then as a statistician, as a researcher, you're constantly learning about the biases that can possibly happen in your data. And one of the best things you can do is have domain expertise about what you are testing. You would have more awareness of what kind of biases can be in your specific data set. Yes, it really depends on the case. And then one thing to also mention is that there is always going to be bias in your data. Well, whatever amount of data you own, it is never big enough to represent the 100%, represent the full population. So you just have to be aware of your limitations.
What about if I balance the data? You said if this bias, what about if I balance the data? Maybe 80% of the data is 0 and 1% is only 1 is only 20%. What about if I balance the data over sampling or under sampling? There will be no bias anymore in that
That's
way.
a great question. That is a great way to remove some of the, most of the biases actually from your data, is balancing it. But it doesn't remove, for example, the selection bias that you might have, that your whole data is from a wrong sample. It wouldn't account for that bias. It wouldn't account for your internal bias of confirmation bias, for example, when you are yourself focusing on the wrong thing when you're doing your statistical research. And the reason that we all know that there is always bias in your data is because even the biggest companies with the biggest amount of data, Google, for example, has still biases in their products. And when they present the product to the public, we can find, as researchers or data scientists, we can find these bugs in the programs, in the models, and say, okay, they have a biased data for this particular thing. Okay.
Thanks for presentation.
Thank you.
But what are the solutions of these biases? I don't know. Like he said that you can oversample or undersample, but for example, survival bias or availability bias, what are the solutions to them?
Right, thank you. That's a great question. So for a lot of these things, there are solutions that you can do. Most of them include adding more data to your samples, having domain expertise, understanding the way that your data is going to be used later to see some of the biases that are possible. There are some very good statistical techniques to see how well your data represents the true population. But for a lot of these things, you just have to know that there are going to be biases, or know that there is a specific bias in your data and account for this limitation. For example, if you have a survival bias, that means that this data doesn't exist in real life for you to test it on. So you are a marketing research person, you are gathering information about the marketing of other companies, and you cannot possibly gather the information from companies who have failed, who are not here to tell us their stories. So you need to write a disclaimer in your research or explain this to the client that you are making the product for, that there is a bias in our data, there is a survival bias, and then we need to take this into account. Okay.
Thank you for the presentation. I would like to ask, as you said, all data mostly that are presented to the public is biased. So how can you rely on the data you find on the internet, and how to choose between the most reliable companies and understand which the data to choose and to test on?
Yes, I presented a very scary presentation. I think I have removed all faith in humanity with this, but the truth is that not all companies are trying to mislead us. And that is a great question, though, because you really always have to do your own research. If you're reading a title that is going to change your viewpoint about a specific topic, you should really read the whole paper. Because we are always getting this propensity to have a clickbait title. So a lot of the researchers would have articles, their papers would have articles that are this huge title that, I don't know, we're dying tomorrow, and you have to click on the paper, read the paper, and see what it's about. Thank you. All right.
Could you please explain again what is availability bias with more examples?
Yep. All right, here. So availability bias is the human tendency to think that things that come in your head easily, examples that you can recall easily, are more prominent than others. So if I ask you a question and you answer the first thing that comes to your head, you might think that this is the most common thing that is happening around you. When in fact you don't have the full data, you don't know if it is or not. The difference between survival bias and availability bias is that for survival bias, the data isn't there, so you can't really confirm. But for availability bias is that you will have the wrong perception about the full data. You haven't seen it. All right. Thank you, everyone.
Thank you too.